In this module, we're going to explore the concept of computational thinking. Now, this underlies all aspects of the digital technology subject, having students think about the world from the perspective of computational thinking. Now, it's similar to scientific thinking or geographic thinking or mathematical thinking or thinking historically. It's a worldview and it's a perspective on the world whereby we see problems and situations and events from the perspective of understanding how computationally they may be occurring. And through that understanding, we can look at the problems that exist that we may want to solve, or the opportunities that we want to exploit to come up with new innovations and opportunities by breaking it down, or by using computational thinking, some of which involves breaking it down through decomposition and other approaches that we'll discuss. But it's allowing students to have a new framework on which to understand what's occurring to them in the world, and that framework is computational thinking. So in computational thinking, we first need to understand procedural thinking. Now, in the workshops, we learnt about doing things in a process or step by step. And coming to see the world from that perspective is the first part of computational thinking, or coming to grips with computational thinking. Because computers do things very, very simply. Okay? They execute commands in the main, one after the other, in a fairly simple, well-defined process that we can understand in great detail. Yes, we've got parallel computing and quantum computing that are blurring those distinctions a little bit, but in the main, computers very, very simply perform a series of simple calculations or processes, one after the other, very, very rapidly. And therein lies their power. They can do things incredibly rapidly, incredibly accurately, and that makes it seem as though they're doing things very, very complexly. But they're not. So coming to that first understanding about computers is the first step in computational thinking, in viewing the world from the perspective of a computer scientist or someone that understands computing in detail. So beyond procedural thinking, computational thinking starts including a number of other concepts. Now, in some ways, computational thinking is a problem-solving process. And there's various approaches we go to solving problems by thinking computationally. The first is being able to analyze and logically organize data. Okay, data is something that we collect in many different ways. We collect lots of data about lots of things. As teachers, you'll collect lots of data about students' learning through tests and assessments and so forth. The census collects lots of data about people in terms of demographics. We collect a lot of data about TV viewing habits in order for the rating systems to work and to give ratings to various TV shows. But throughout the world, there is an immense amount of data being collected. A lot of scientific data is being collected, a lot of weather data, and from that we can then learn about the world. So being able to actually collect data, analyze that data, organize it, is the first step in computational thinking. So seeing the world as a source of data. Now that is difficult for many people to get their heads around, and it's something that you're going to have to get your students' heads around through various activities and learning projects that you'll be able to engage your students with. Now the next is what we do with this data. It's easy enough to collect lots of data. Okay, there's literally trillions of gigabytes of data being collected each year, but most of it is never analyzed or organized, or never actually used. So once we've got this data, we can then model things. Okay, modeling is whereby we take data to represent an aspect of the real world. So for example, creating a weather map. Okay, the weather map might show the temperature of various places around the Gold Coast over 2 years. Now that's modeling temperature. That's modeling a real world event whereby the temperature has changed in the real world over 2 years, and the model that we create is simply a map and some numerical information about various locations representing the temperature that occurred in the real world at those times. And we might be able to turn that map then into a graphical representation showing a heat map whereby the different temperatures are shown in different colors and they may change over time, and so it gives an accurate little simulation of what occurred with the temperature on the Gold Coast over those 2 years. And we could then change those values. Maybe we could, we'll talk about simulations a little bit later, but the idea is now we're abstracting that data. So we're taking a real world event, which is temperature, and that's quite a complex thing. And there would be different temperatures every few meters, potentially. But we're abstracting that by taking temperature readings just at certain locations, and we're abstracting the complexity of how that temperature occurs and all the different variations in temperature down to a single number that we're then using to represent the temperature of that location at a particular time. Of course, now we've got a simple set of data, a simple set of numbers that represent temperature over that time. Now we've abstracted the real world processes that occurred with all the temperature and the sunlight and wind and all the rest. We've abstracted all that down just to a couple of numbers that represent temperature. We can now manipulate that and use that to give an understanding of how temperature changed over time. So that's data modeling and data abstractions, and we're going to talk lots about examples of how we can explore those concepts. Now that we've got some information to work on, we can try to solve some problems. So the problem might be people are getting too hot. So it may be really useful to understand why is the temperature different along the beach than in certain suburbs. There might be certain suburbs where it's a lot hotter than certain other suburbs. So this then starts giving us a possibility of modeling what's occurring. Why is it that certain suburbs are hot and other suburbs are relatively cool? It might be to do with the wind. It might be to do with, there could be a range of other things. Generally it's the wind, but we might create a simulation then to test whether or not that's actually the case and look at, not just collect data about the temperature, but also data about the wind. And then by putting that into the computer, we could then change the model that we create, and if we've made it interactive, we could then adjust the actual wind conditions in certain locations and see how that would change the data based upon a model that we've created that is incorporated all of that information that we've got over many years, which might have various wind conditions and data and temperature associated with them. Putting that onto a map allows us to visualize that, and we may be able to see that if the wind is high or if the wind is flowing through a particular suburb, then it keeps it relatively cool. If there's no wind flowing through a suburb, maybe because of some hills or other things, then the temperature may be very high. So that would then assist us now in solving a problem. So one approach might be to have some way of redirecting the wind into a suburb. That might be a bit too complex, but it allows us to at least understand why the problem is occurring. Doesn't necessarily mean that we might be able to change that, but we can certainly explore how we could then maybe adjust where people live depending upon where the wind flows. It might be very important that if we build some more skyscrapers, that might block the wind. And we may find that we have new suburbs appearing that become very hot because the wind flow has been blocked. Or we might be able to adjust where our tall structures go to channel wind. And we might be able to make then a computer model that could allow us to explore those things. So this is where we start looking at how the computers can assist us in solving those problems. So if we never thought about data in this way, if we never thought about collecting lots of data and then using that to analyze problems and explore solutions to those problems, then we might just continue suffering along, getting hot and having more and more buildings built that might block the sunlight. Or we might discover that the temperature is related to the number of buildings in a particular location, or the amount of asphalt or roads and car parks that are in a particular area. And that suburbs that have the majority built up without a lot of green space may be hotter than suburbs that have lots of parks and open space. And that may be very useful in solving problems. But unless we start looking at things from a perspective of data, then we can't really look at addressing those. But of course, once we've got our concept and we can think about how to model that, then we can start putting that into a computer program. And we could then adjust, okay, what if we increase the green space? If we make assumptions that by increasing the amount of green space that it will get cooler, and we create a computer model that shows that, we could then try that out and we could go and look at other towns, and if they've got lots of green space, does their data show that the temperature is less? Does our model that we've created actually reflect the real world? That's where we get into identifying, testing, and implementing possible solutions. So one big aspect of computational thinking is creating models of the real world and seeing if they then actually relate to the real world or not, and trying to improve our models. That's what climate scientists do all the time, and certainly those that work in the stock exchange, and lots of scientists are about creating computerized models that represent the real world and adjusting those and improving them to more and more accurately reflect what occurs in the real world. But that's just one approach to computational thinking. Another approach is to look at automating solutions. So, for example, we might decide that putting up shade cloths could adjust the wind. So this occurs in places, say, where they have flooding. Let's take an example of the London, and at the entrance to the Thames, the main river that flows past London, they have problems whereby when there's high tides and tidal surges or floods occurring inland, then London can flood. So they've created a very large gate that blocks the river to prevent tidal surges and water coming up the river from the ocean if there's particular weather conditions. Now, the decision as to when to close that or not is very complex. And so they've built various automated processes to analyze the weather conditions and to make decisions as to when and how much to close various gates. A similar thing could be here in Brisbane, where we've got our algorithms that they're now putting in place to decide when to release water from our dams to prevent Brisbane flooding. Now, an algorithm is simply a process of decision making, or step-by-step process resulting in some sort of outcome. Now, in many cases, they're manual solutions whereby we make those decisions, but they can also be automated or computerized. So you could imagine a system whereby it would measure the amount of rainfall occurring in various locations and then automatically adjust the amount of water being released from the dam depending upon those particular algorithms or those particular models. Now, if we've got the luxury of time, we could leave those as manual processes. Human beings could make them. Of course, you've then got the potential problem of influencing factors, or human error as it's commonly known, whereby it might be politically difficult to make those decisions because of the impact upon the floods. So automating them can be a way of getting around that. But the main reason for automating is when we want to do things more quickly or more efficiently or more accurately. So, for example, once upon a time, there used to be people standing at the traffic lights, at traffic intersections, policemen holding up their hands and letting traffic through depending upon which way they're holding their hands up and which way they're telling people to go. And that still occurs in many parts of the world, where you've got traffic police that actually direct traffic through intersections. Now, of course, that is a fairly complex job, and sometimes the traffic officers do make mistakes. They might accidentally have to scratch their arm and suddenly the traffic's colliding. Or they just aren't able to cope with the various speeds, or sometimes just get bored, or other things could go wrong. So automating that process by putting up traffic lights and having the computer determine when to change the lights to allow traffic to flow in various directions was seen as a solution to the problem whereby people had to do it manually. So there's a range of other potential processes that students can come up with that can be automated by computers or by digital devices to implement an algorithm. Sometimes, of course, they want it to be more accurate. For example, say detecting whether or not well, I've got a friend that works at the milk factory, and one of his jobs is to manage machines that detect whether or not the labels that have been applied to the milk cartons are within a certain fraction of a millimeter aligned correctly. And if they're not, then there's a computerized device that will knock the milk container off the conveyor belt so that it doesn't get processed through. And literally hundreds of thousands of milk containers are going through every hour, and on average a couple of hundred are knocked off the conveyor belt because the stamp of the date is slightly inaccurate in terms of how it's been placed on the milk container. Now, once upon a time, that would have been a job for someone to do manually. And of course, they couldn't do it at 100,000 milk bottles an hour. They would probably have to do it at less than 1,000 milk containers an hour. So there's been efficiencies achieved by computerizing that process, where it can now go much, much quicker because the computerized device is more accurate and able to read the potential inaccuracies more quickly. So other automated solutions can be achieved through algorithmic thinking. So we can not just automate these sort of processes, but we might automate more commonly applied things that we would like to do, such as, say, sending an email. Now, once upon a time, to do that on a computer, we would have to create a text file that had our information in it, and then we'd have to use another program to upload that text file, convert it into a series of digital signals, or zeros and ones, or binary, that we could then transmit, and then another program often to do the actual transmission. And there were multiple complex processes we had to go through in order to achieve the task of sending an email. Nowadays, they're all combined into one algorithmic solution, whereby the computer knows what has to be done in a series of steps, and instead of us having to do them individually, we can automate that process. Some things that we still do in complex ways might be, say, converting images to go onto a web page. Often, to put an image onto a web page, we have to use another image program to create the image. Then if we want to make the image as small as possible, we might use another program to reduce the size of that image down to as small as possible. Then we have to upload it to the web page using another program, and then place it on there and check it all out. So having all that done by the web page software would be a way of improving that efficiency. But at the moment, it's still done by several programs, and so we've still got some efficiencies that can be improved upon. But I'm sure that over time they will be. And finally, the last aspect of computational thinking is being able to generalize and apply these processes to other problems. So let's say the problem of the traffic lights. We think we've had traffic lights around for a long time now, and the idea is there that it's simply a process of stopping and starting and on a timer, allowing things to occur or not occur. So generalizing that, we could then explore how that could be applied to other situations. So let's say a simple direct application might be when students are lining up to get or put their books away at their port racks. Allowing everyone just to rush in there and do things automatically would cause chaos, and often does in schoolrooms. So having a system whereby each student lined up, and then every 10 seconds they were allowed to go forward, and then next student had to wait 10 seconds before they were allowed to go forward, then the next one had to wait 10 seconds before they were allowed to go forward, would potentially improve the efficiency of the system. So instead of everyone rushing in and doing it at once, we could allow students in with a wait between each of them, and that may get them all out collectively more quickly than if they all tried to do it at once. So that's taking the generalized concepts that we've learnt from traffic lights and applying them to other situations. So they're the fundamental aspects of computational thinking. So you can see that they're not particularly complex concepts, but the fact that we don't really think of the world in that way most often means that we're not thinking computationally. And thinking computationally allows us to approach problems in ways that we wouldn't if we didn't think computationally. Okay. So, there's another 4 basic concepts in computational thinking. The first is decomposition. This is where we take a problem and try to decompose it down to identify the fundamental bits that make up the problem. The example there is taking an item of food or an unfamiliar food dish and breaking it down so we know the individual ingredients that make up that dish. Being able to decompose a problem is very important, because sometimes it's one of the small parts of a problem that's causing the issue, or small parts of a system, as we probably more easy to define it. Simple thing would be thinking about your TV set. Okay, we come to a TV set and it's not turning on. So if we just thought about it from that perspective, it's broken, we've got to go get another one. Or we could say, okay, is it maybe the remote control that's not working? Okay, maybe it's that. Maybe it's the batteries in the remote control that aren't working. Maybe it's the little connector that connects the battery to the remote that's not working. And if we can see that that's the problem, then we might be able to solve it. So instead of throwing away the entire TV set, we might be able to just fix the little connection to the battery and address the problem. And we do that through decomposition, breaking down the problem into smaller and smaller parts until we can understand the actual issue that's causing the problem. Another concept is pattern recognition, where we look for patterns in the data. Okay, a very important concept. We talked a bit about that when we looked at the idea of temperature across the Gold Coast. So being able to see that there's certain patterns related to the wind and the temperature allow us to understand the problem. Pattern generalization and abstraction is where we now take those patterns and we generalize them. Well, firstly, to be able to computerize them, if we want to do that. So being able to take a couple of data sets, say a few points around the suburbs where we collect the temperature. So instead of collecting temperature for every single millimeter across a whole suburb, we can collect them in a few locations. Okay, that allows us then to generalize that data. That allows us to abstract the data. So instead of having to do everything and make it just like real life, we can simplify it down by reducing it in some ways. And then we can generalize. We can apply our understanding, often our model that we've created to understand something, and generalize that to other situations. So the example here is that a daily planner abstracts a week in terms of days and hours. So it breaks up a week in terms of a series of days and hours that we can then use to understand and organize our time. And so instead of breaking it down into milliseconds, we've abstracted it down to hours or days and things of that nature. And finally, we've got algorithm design. This is where we create a series of instructions that others can follow. More often, we use it for computers to follow. So, you're starting to get an idea of the basic concepts of computational thinking. There's a number of videos you can look at to get an understanding of. We'll go into some technical terms here about prefetching and caching and backtracking and so forth. Don't worry about those at this stage. They're computing terms. They do become useful as we get a greater and greater understanding of computational thinking and computing. But to start with, the basic concepts are what's important. A few different characteristics of computational thinking, where we think predominantly around conceptual concepts, not programming. Computer programming is the tool we use to implement our ideas, but it's not the ideas. Okay? Without the ideas, without being able to conceptualize the world from computational thinking, computer programming would have no point. So if you just teach computer programming without the concepts of computational thinking, then computer programming becomes a trivial aspect, a bit like how we teach mathematics in schools. Without providing it with a good context, mathematics is simply something that doesn't have any contextual basis for a lot of people, and they don't see the use of it. Same as if you taught programming. Without the computational thinking approach, then it would also be difficult for people to contextualize and apply to their lives. Okay. So computational thinking, again, is not the way computers think. Computers think very, very specifically and following very, very set specific processes. And at the moment, they can't abstract. They can't do all the things that we think about computationally. People are working on making computers that can do that, but for the moment, they're a long way from that. And so computational thinking is the way we think. So it's our way of thinking about the world in terms of computationally. We can then use computers to enable us to do some very powerful things because of that thinking, but in itself, certainly we're not learning to think like computers. And of course, computational thinking does rely upon a fair amount of mathematical thinking, and there's no apologies for that. It did develop out of mathematics, and computational thinking is still part of some studies of mathematics. But the way we're looking at it in digital technologies is much more from an applied approach to problem solving than learning about complex mathematical concepts. Okay. So you can read through those other aspects there. I've given you a whole range of lists of aspects of computational thinking that people have come up with in terms of trying to define exactly what computational thinking is, and you can explore those and get a bit more of an idea of the breadth of what computational thinking can include. So some of the big concepts, it's a lot to do with creativity and about fostering creativity, and particularly the use of artifacts for creating, so using computers and being able to use digital tools to be more creative. Not necessarily in terms of the creative process, but in how we can actually think about different ways of applying digital tools and digital technologies and computers. Because computers are still very, very new, less than 50 odd years in the main. So there's lots of opportunities to come up with interesting and engaging and potentially lucrative new ways of using computers. Facebook didn't exist 10 or 15 years ago. There's lots of new technologies that have emerged, certainly in your lifetimes, and certainly in the lifetimes of some of your students. So it's very exciting to be at the cutting edge of new technologies, whereby students can feel, and indeed are, able to actually contribute to innovative new ways that we can actually express ourselves and explore the world through our use of digital technologies. So the creativity aspect is very important. Being able to abstract means we can focus our thinking. Okay? It can actually help us become better thinkers by thinking more in terms of abstraction. Of course, by being able to simplify things, to be able to take complex situations and concepts and so forth, and abstract them down to their simplest nature, can be a very useful tool for students where they are faced with a very complex world. And the world's just getting more and more complex. So being able to abstract that world and create an understanding of it in a simplified way can be very, very useful. Particularly if you've got students on the autistic spectrum who really need to abstract because the world itself is just too complex for them to actually cope with in many situations. Being able to abstract that is very useful. And again, this is where computer games and simulations can be very helpful, because by their very nature, they are often an abstraction of the real world. And so being able to understand a computer game, for example, means that we can then apply that understanding to whatever it's modeling about the real world. And likewise, we have simulations that do the same process. Okay, we've talked a lot about data and how we can use data to create knowledge. So being able to actually take in lots of this raw data and apply it in different ways means that we can then have a greater understanding and knowledge about the world. Collecting all the information about how students get to school and the different ways different types of transports they use can be a great way of understanding what the situation is for students. Do we need better roads? Do we need a better bus stop? Are parents spending a lot of time trying to drop their students off at school? These are all problems that students could look at solving by collecting lots of data about the transport situation and then trying to come up with solutions for that. Now, it may be using a computer model to better understand what's occurring and using that to solve the world or the problems that exist in the real world. Or there may be digital solutions. Creating an online database whereby parents can carpool might be one solution. It might be looking at the map data and working out where other roads might be able to be built that would help address the problem. Or it could be a traffic light solution that might help manage traffic flow into and out of the school. There could be a whole range of different potential solutions to the problem that students might engage with in that context. We've talked about algorithms and about how we can use different algorithms to program a series of steps to help overcome problems. And again, sticking with the traffic problem, there may simply just be an algorithm that could be applied. And if we get parents to drop students off at different times, so all the parents that have last names beginning with A to F drop students off from 9 till 9:30, and then all the students with other surnames drop them off in a sequence of other times, and that may ease the flow of the transport coming into and out of a school. Okay, simply through the use of an algorithmic solution. And of course, creating computer programs allow us to then take our algorithms and apply them in a digital way, and often that can be then very quickly processed or very accurately processed to address particular problems. So a range of other concepts there, particularly around the global impacts of digital computers and technologies, how some areas are losing employment but other jobs are being created. The idea of cybersecurity and potential issues around bullying online, but also how we can use computers to track what occurs online and address issues around bullying. So there's a whole range of different concepts that we can use with a greater understanding of data and how it's used with computers. Okay, a couple of more specific examples again. Decomposition, and I've given you some examples there where we can decompose things. When we give directions to our house, we decompose the process of getting from one place to another. Okay, we give them a set of simple instructions. So instead of taking down exactly how they're going to physically move from one place to another place, how they're going to move their legs, how they're going to, what they're going to see along the way, all that sort of potential complexity of information, we're decomposing that down to simply a set of instructions that said, okay, travel along here until you see this, then turn left until you see this, then turn right until you see this, and then you're there. So it's a much simpler set of instructions than if they had to engage with the whole complexity of... So one way of thinking about it is, what would we have to tell a blind person to get to a location? We'd have to tell them a lot more about how to actually move from one location to another location. But if we decompose that down to someone that can visually see various indicators, we can then tell them about those indicators, such as signs along the road or numbers at the house, and they can use that then to very quickly get to the location. And then, of course, there's various uses of decomposition in mathematics, and that can lead then into applied uses in terms of computer programming. Pattern recognition, again, various processes that students can use, such as identifying patterns in the reactions of their parents and their teachers to their behaviour. Students are quite good at testing boundaries and then looking at the patterns of behavior that then result from that. So if they discover that, okay, they might be able to do something, say they can take 2 cookies from the cookie jar and no one seems to mind, but if they take all the cookies from the cookie jar, they seem to get in trouble. So there's a pattern that they've identified, and that can then change their future behavior. So we can look at patterns in the world and then look at what the impacts of changing those patterns might lead to. Then we lead back again to pattern generalization and abstraction. So for example, the world map being an abstraction of the Earth. And we can then use various maps to assist us. So back to our problem of getting from one location to another, having an abstraction of the real world in terms of a map, where it might be just a line showing a couple of angle changes which represent turnings along a road, gives us an abstraction of the real world so that we can then help us navigate. Algorithm design we've talked about. Again, you can look at all the different examples. Now, to help us get an understanding of all this computational thinking, we've got various tools. One set is, of course, programming languages, programming tools, where we can apply that. Another is robotics, where we can program the robots to do various things and help us understand these concepts. I've given you here a set of computational thinking illustrated, and here they've got an artist that's gone through and they've drawn various pictures to represent different computational concepts. So this one is using abstraction and models, whereby we take example of the real world robot and abstract it into a little toy robot that we can then manipulate ourselves. So here an abstraction of a car might be a toy car that students can then manipulate and move around and draw up a little city map and move it around a city and look at the different traffic congestion that might occur. So they could make an abstraction of the traffic situation in a school using toy cars and a map that represents the real world situation of the traffic chaos coming into and out of the school. Another one here is analyzing problems and artifacts. So trying to understand how various tools work and how problems are resulting by analyzing them and using decomposition and other approaches to break down those problems. Communicating is another process in some aspects of computational thinking, and in letting others know about a situation by writing that down or drawing diagrams or creating computer programs or illustrations to communicate ideas to others. Working in teams is sometimes seen as a computational thinking process, and how we can improve that. Of course, it often involves a lot of abstraction and processes whereby we do things in sequences or assign tasks and model various aspects of how the group works. Decomposition we've talked about, breaking things down to better understand them. Pattern recognition, looking for various patterns and how they combine, or how problems might be identified where the patterns are showing something that wasn't expected. And then recognizing those patterns and being able to generalize them and abstract them. So for example, how we use a whole lot of patterns to make up what we see on our computer screens. So here we're using little binary bits and with pixels being on or off to represent a picture of a house. And then algorithms design, where we use a sequence of instructions to perform various actions, in this case representing a dance step. So finally, I've given you here a collection of computational fairy tales. There's a whole range of storybooks being written to help teach computational thinking, but this is a collection of them. Some of them are quite complex, but there's a number of basic ones that can help you. And as you come to try to explain various concepts to students, certainly the more advanced ones you wouldn't explain to students generally in primary years, but some of the beginner ones certainly would be useful around teaching about loops and decisions, or if-then else's or if-else's, searches and so forth. And there's a whole range of stories that you can use to assist you in explaining these concepts to your students. So that's a bit of a summary of computational thinking. We're going to be exploring these in more detail as we look at computer programming in increasing detail over the next few weeks. But remember, it's about seeing the world from the perspective of thinking computationally. We then use various tools to assist us in solving problems related to that thinking, particularly computer programming and maybe manipulation of hardware, creating things with makey-makey interfaces, etc. But underlying it all is the ability to think computationally. That's what you need to get a grip of, and that's what you need to impart to your students as you do the various activities associated with digital technologies.